Okay. So, please.
It's thank you very much, and it's a joint work made with Gregory Futazar and Lalao Hakoto-Manana, and it's a work on Riemann-Cartan geometry applied to mechanics and typically in elasticity. In fact, we have tried to make link between the situation when a wave C medium with overall defect in all the medium, and the situation where a wave meets a single discrete defect. So I will begin with some physical interpretation on defect, and as you already know, there is a typical defect that is called dislocation, and dislocation, here you see a typical classical elastic medium, and here it's the same medium with a dislocation, what we call an edge dislocation. This dislocation can be seen when you ask to somebody to make some step, for example from the bottom to the top, and if this guy makes a fourth step, he go from Q to P, and if he make a fourth step from this situation, he go from N to M. But if this guy make four step from Q to N, he go in. He does not close the parallelogram. If he makes the same number of steps, he go only from P to Q. So there is a small vector who close the parallelogram from M to Q. This situation can be seen also in a screw dislocation, and where the same process can be performed, and the picture shows this phenomena. In fact, what we have seen here in the case of a crystal can be generalized in a continuum, and in this case what you have to do is to cut in a half plane the medium, and after to push a part of the medium and to glue it again. In this case we can measure the same Berger vector, here for the edge dislocation, here for the screw dislocation. This Berger vector measures the slope of the displacement vector along a closed curve. In fact, there is several tools to introduce this Berger vector. If we use the geometrical tools, we can introduce the torsion density, which is the same Berger vector is obtained by a measure of a surface density that is explained here, and in fact it's almost the same quantity that we have in the Nye theory, where the Nye tensor, a 2 tensor, is here. In the work we have done, we are trying to understand what happens when there is a small perturbation, a small wave superimposed to a media with defect. And so, in particular, we have tried to solve this type of problem. We have an incoming wave which belongs to an perfectly elastic medium, and this incoming wave meets a domain with defect here. So this will be introduced, some scattering and some transmitted wave inside. And we have tried to observe what happens in this situation. In classical elastic theory, we can, for example, use books from Marsden or a lot of others, and we have a transformation which is a map from the referential situation to the actual situation. And if we want to compare vector, we have to introduce the gradient of this map. And so we can link the vector, the actual vector, with the referential vector thanks to this gradient. But we can link also the relative length dx thanks to this gradient. So this is the main tools to make elasticity in the general situation. And in fact, thanks to these tools here, we can measure the new metric and the strain. In fact, we can relax this general situation by introducing another quantity here, which is not a gradient. So in this case, what does it mean? That I have introduced what we call sometimes a triad, which relates the two small distance in the reference situation and in the actual situation. We can obtain the reciprocal triad by this way and obtain the metric by the same way. After that, the strain is measured by the same, with the same tools. In fact, what we have to keep in mind is that the triad is not a static quantity and is not a uniform quantity. If it's a smooth quantity, we are in the situation of elasticity. But if it's a continuous piecewise quantity, we are in the situation in plasticity. And if it's a generalized function, like a distribution, we are in the situation of dislocation. So, I will introduce some general function for this quantity here, and perform all this work. So, what we have to know before, it's thanks to this triad, we can write down the covariant derivative. And this is right down here. And what we see here is that the connection is defined by some coefficient, which is right here. These coefficients are not the Christoffel symbol, because they didn't have a symmetrical part for the two lower indices here. The Christoffel symbol are right with a bar over there, and the general connection is right here. So, in fact, the difference between the two connection symbol with a switch bottom indices is the torsion tensor introduced by Cartan and used also by Kroner. The compatibility situation corresponds to the situation where this torsion is zero everywhere. And in fact, this torsion measures the non-holonomic character of the transformation. That means that when I make a parallel transform of a vector along a line, like that, and a parallel transform, a parallel transport of the other vector along the other line, I don't close this cube, this square. So it's almost the same situation that we have obtained in the case of dislocation. So, thanks to this new connection, we can of course decompose linearly this connection with first the classical Levitshevica symbol and another term, and this term is called the contortion. And according to these things, we can linearly decompose the covariant derivative with the contortion here. The contortion is related to the torsion, and the Christoffel symbol is related to the metric only. If I write down all the terms of a curvature, what we observe is that in fact the total curvature of the medium, the generalized medium, is the classical Riemannian curvature plus some other term. Here you see that these terms are related, the two red ones, are related to some spatially variation of the contortion. So if I have a uniform contortion, I don't have this term, but only these two terms. That means that even in a flat medium with a uniform torsion, I can have a new curvature. Okay. So, what we will do now is that we will write down the classical elasticity thanks to this generalized geometry. So, I will suppose a reference state which is Euclidean, and I will introduce an infinitesimal transformation thanks to the triad. This transformation, of course, must be what we call metric compatible. So this means that we don't build up whole. This can be seen like that. So we have this type of mapping of the medium. And so the main tools of my geometrical description is first the torsion, which is first the metric, second the torsion. These two tools are independent. I can choose them independently. And the main mechanical tool to write down the equation is the new connection with the classical connection and the contortion. Okay? So, a typical triad defines a torsion, which defines a contortion, which defines a new connection. And I will write all my mechanics with this new connection. In fact, what we want to study is a linearized problem of wave. We superimpose a wave to a plastic transformation. So we have a plastic transformation, and after we make a small modification, a small linear modification. So we suppose that there is no energy introduced by a modification of the dislocation of the triads. We suppose that the contortion does not depend in time, and so we have only this small conservation law for the mass, for the momentum of conservation. For the Hooke's law, we have only energy, the elastic strain energy, because the wave does not introduce new plastic transformation. And we have the classical linearized strain tensor. All these equations are right with this connection. So after, in order to write the Navier equation, I just have to put this term here and this term here, and develop all the situation thanks to this new connection. Finally, I have the classical Navier equation plus here F, a configurational force. This configurational force have several terms, and what we see here in red is the term coming from the curvature induced by torsion. So I will this pitch color force is too complicated, and so I will simplify the hypothesis. I will suppose that the medium is Euclidean in the reference situation, that we have a Cartesian coordinate, that we have a uniform torsion, and even with all these things it's too complicated. So I will introduce an idea that I have only one type of torsion which is related to a uniform density of screw dislocation. In this case, I have only this non-null term, and in the following I will call it S. So, thanks to this term, I write the contortion and I clean up all this equation to obtain this one. Of course, this wave equation, this Navier equation, is a wave equation, and we have here the term induced by curvature, and here the other term. The term CL and CT are related to the longitudinal and the shear waves. What we can see in order to understand what means this equation, we can suppose that we have we can focus on the term introduced by curvature. What we see, it's, for example, if I solve the linear problem of a rotational static plane strain problem in a 2-3 direction without defect, I know that the static field solves this equation, the black one. So all these terms are 0. But if I am in the situation where there is some defect, we can see that is 0, give a 0 term here, but not a 0 term here. So we have a non-null time dependence to have to introduce. And finally, we have this time dependence. It can be right like that. Acceleration is related to curvature. Okay? And in fact, what does it mean? It means that the statical problem obtained without defect, so here it's a longitudinal displacement, is perturbed in terms of wave, in terms of defect by time variation. Okay? So we have this breathing mode, which we see is related to the curvature. If I understand all the other terms, I can in fact impose a harmonic plane wave solution with a frequency omega and polarization u. And in this case, if I want to impose a direction of polarization, I have to find a key which must solve a dispersion relation, which is right in a matrix in a matrix form like that. So I inject this form here, and after I write it down like matrix problem. And in fact, there is various key which solve this problem. These keys are not independent of the direction of the propagation according to the Berger vector. Here you see the situation where the propagation, the plane wave, propagate in the same direction than the Berger vector of the screw dislocation. And you see the dispersion relation. You see two almost shear wave here and one longitudinal wave in this direction. Here this line corresponds to the shear wave without defect. This line corresponds to the longitudinal wave without defect. But if I move and see which plane wave propagate with a small angle according to the Berger vector, I see that the dispersion relation change and introduce some other wave number. Here what I have seen, what I have shown you is the real part of the wave number, but in fact the wave number is complex. What you see here vertically, this is a situation where you have a zero group velocity. That means that the energy does not propagate. What you see here is something that I don't really like. It's a situation where you have an infinite group velocity, which is something special. But in fact, this term here is related to a complex wave number with a non-null imaginary part of the wave number. So globally, with this model with an elastic media with torsion, we can observe breathing mode, anisotropic propagation, we can observe infinite group velocity, zero group velocity, we can observe attenuation limited to the low frequency regime. This attenuation located in the low frequency regime is quite classical in geometrical elastic medium, like in the Timoshenko beam, where you have a complex wave number in the low frequency regime. So the large density of defect does not mean attenuation in the high frequency regime for geometrical defects. If you go to the high frequency regime, what you see is that the wave number supports a shift according to the classical wave number Kt. This shift, kappa, is related to the angle. It's not the same when you change the direction of the plane wave according to the direction of the Burger vector. And in fact, if you check the polarization, you observe a chirality related to this shift. This chirality means that when you are in a medium with defect, what you observe is a wave which have a typical wave number, very high frequency regime, so with a millimetric or maybe less wavelength, like that. But when this propagates on a long distance, you have a chirality aspect. That means that the polarization changes slowly during the propagation. Maybe this is due to a cumulative effect of the density of the effect. And what is sure, it's not related to the curvature, it's related to the other linear part of the torsion. And what we see too is that this effect, what we will be interested in is if somebody knows some experimental validation of these things. I will be very interested. I don't have found this type of validation. Okay. So now I will be interested in the case of a screw line dislocation. I have a screw line dislocation, and in this case I have told you that it's a generalized function. The torsion is a generalized function. So that means that the torsion can be modelized like a uniform torsion on a disk of radius A, and you, after solving the problem, you impose A to be small, 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 small. Okay? And so you write, by this way, a distribution. So I will solve this problem in a very simple situation where I have a plane wave propagation in a plane wave propagation in the 2-3 plane perpendicular to the Burger vector. In this case, we can show that the pitch color force is very simple with a term related to the curl of the displacement, and another term which is related only to the in-plane field. We can prove that this field, in-plane field, supports an L-mode decomposition, and after we can prove that the shear field, the shear potential here, is coupled with the transverse displacement. That means that we have broken down the classical decomposition of the PSV-SH problem, PSV-SH 2D problem of scattering. If I send a longitudinal wave in this direction, in elasticity, I will observe a shear and in the same plane, and a longitudinal wave in the same plane. Here, I will observe something else, which is a transverse shear wave. So, first we have to write down all the equations. So outside the body, I will impose an incoming wave, which have this type of coefficient, and which is write down thanks to the Bessel function with the classical wave number. For the scattering wave, it's almost the same things, and inside I have to inject the typical wave number in the medium with dislocation, with defect. So after, the scattering problem reduced to the situation to solve this scattering problem, which is a linear problem, and so we obtain the modal amplitude according to the known source term, which is related to the incoming wave. In fact, we have to impose A going to 0, but this can't be done mathematically, theoretically. We have to impose a ratio which go to 0. So we have to impose A going and we keep fixed the Burger vector. So S will not be constant during the asymptotic procedure. So we have a modeling which is related to three lengths: the length of the Berger vector, the distance, the size of the dislocated domain, and the wavelength here for the shear wave. And so, in fact, I impose this typical ratio going to 0, but I do not know what about the other ratios which are possible. So I have solved for you one situation where this ratio is 0, going to 0, small 1, here it's 1, going to 0, and this one is finite. In this case, what we observe is that the total displacement in the inclusion is the superposition of three things. If I impose an incoming shear wave, transverse wave, the displacement inside the inclusion is the incoming transverse wave plus a term which is a uniform displacement in the EY direction. So my density of dislocation move in the plane. And this will produce a scattering which induce some far-field radiation which are not related to A, but which are related to the ratio B over L. What we observe is that we have killed, in fact, the SH. We have injected a SH polarization and observe a PSV radiation. I show you a simulation of the effect if you want. If you don't want, I show you too. Okay. Here you see the dislocated domain, how it reacts according to the shear vertically wave. And you see this moving, this motion. And after, you can impose exactly, not exactly, but almost the other problem which is, you impose, a longitudinal wave, and in this case, the displacement inside the inclusion is a vertical displacement but with Y, so in fact it's a rotation according to the direction EX, and a uniform horizontal displacement. I show you another simulation because it's more simple to understand. So incoming longitudinal wave induce this type of motion of the dislocated media. What we do not have introduced any force which move the dislocation line. We observe it only by introducing torsion. Okay? So that's the end of my talk, and in fact it's a preliminary work, and I will be very happy to have constructive question and discussion, and in fact just we are trying to go more further to make some connection with other model, and we will be very happy if some people can propose us some paper where there is some experimental validation of this type of phenomena. We have a paper will appear soon, and keep in mind only this thing, we have a lot of effects, only one with one ingredient, the torsion. And here I have imposed a uniform torsion, I have imposed only a screw type torsion. I can enrich the medium by a more large torsion tensor. Thanks very much. in which part of the work? Because in fact I don't have introduced any limitation in the first part of the works. Okay? But after, when I show you the problem with a single dislocation, I have imposed that the wavelength is very larger than the size of the dislocation and make my asymptotics according to this situation. No, I don't have claimed that. No. What I have said is that a uniform torsion density will introduce a rotation of the polarization on a long distance, but it's not exactly the same thing. Because it's a uniform torsion density. There is a lot, not one.
Did you say that when you impose a constant torsion, the
I have said that when you have a uniform torsion, when you have a torsion, you introduce curvature. When you have a uniform torsion, you introduce curvature too. I have said that.
propagation is due to curvature?
The propagation is affected by the curvature. Not in the high frequency regime, but in the low frequency regime. No, because it's a linear problem. So, in order to simplify the equation, I impose the amplitude of the incoming plane wave was 1. But whatever the amplitude, the displacement is proportional to this amplitude. It's a linear problem.
Why is there so experimental evidence?
Sorry?
Why is there no experimental evidence?
Because maybe I don't know how to, in which literature I have to go. I think it's my fault. Maybe there is some, but I don't find them.
Just a small question, just to understand better what you are doing. In the end, it's a linear problem with a certain homogeneity given by the torsion. Is that what you're doing? So, okay, it's a linear problem with the homogeneity.
It's a linear wave outside the dislocated domain. It's a classical elastic problem, a classical elastic medium. And inside, there is a medium with a density of torsion, uniform one. And it's a linear problem in all the case. It's a linear because I've superimposed a small displacement to the plastic transformation which have been already imposed. That's why. And because the plastic transformation does not move with the time.
This one is fixed?
Yes, torsion is fixed in time.
Yeah. Okay.
That's why.
Thanks a lot. You have seen that almost
What do I do with this?
somebody else is hopefully here. We're coming from a different background. So,
Can you help me with this?